In the next examples, we're going to look at solving systems of inequalities by graphing. So systems of inequalities means that we're going to find all of the ordered pairs that satisfy the inequalities in the system. With inequalities, we're going to have an infinite number of solutions, or we're going to have no solutions. Or if there is a boundary line, we still have an infinite number of solutions, but we could just end up on the same boundary. Our key concept, what we're going to do is we're going to graph each inequality. Probably our simplest way of graphing is to put them in slope-intercept form and then graph slope and y-intercept. There are other techniques of graphing lines. You could use your x and y-intercept method as well. One of the things that we want to be aware of is whenever they put in a less than sign or a greater than sign, we have to use dashed lines, and whenever they have a greater than or equal to or less than or equal to, we have to use solid. So in summary, anytime we have less than or we have a greater than sign, we have to use the dashed lines. That represents we will not include the boundary line because anything on the boundary line makes those two systems equal to each other. Whenever we have less than or equal to or a greater than or equal to symbol in our system, then we're going to need to make sure that we use solid lines to represent the boundary line is included in part of the solution set. So dashed lines means we do not include the boundary. Solid lines mean that we do. So what we're going to do is we're going to come back and we're going to look at the first example, number 6, and then I forgot the step 3. We want to check the solution by a test point within the solution region. And what we do is we shade the point of our graph where we want the solutions to be. And we can test a point, and typically 0, 0 is your easiest point to put in there at the origin. So example number 6. The first thing I want to do with this first equation, I'm not a big fan of decimals when I'm graphing. So instead of putting a half, I'm going to put a 1 over 2 times x minus 3. The reason I like to see that is when I see the top and the bottom, I've got the change in y over the change in x, the slope. So when I'm thinking of our slope formula, it's change of y over change of x. Now I have the y's changed by 1 when the x is changed by 2. So the y-intercept says we're going to start our graph at a negative 3. So I'm going to go down 3 units, and that's a point on the graph. The negative 3 is our y-intercept. From there, we're going to use our slope, and we're going to go up 1 unit up 1 unit, and then 2 units to the right. So 1, 2. So there's another point on our line. 2 points is all it takes to make a line, and because it's greater than or equal to, I want to go and use one of these solid lines, and now I'm just going to graph solid lines here through my 2 points best that I can. Okay, so there's a representation of where that line goes. Now we want to be greater than or equal to this line. I'm going to apply a test point to this, and as long as our line doesn't go through the origin, I'm going to use the origin or the 0, 0 as a test point. I want to put in 0 for y and 0 for x in this equation. Is 0 greater than or equal to a half times 0 minus 3? Or in essence, is 0 larger than or equal to a negative 3? And because that's a true statement, what I know from my graph is I want everything that is above or on my boundary line. So I just took care of the first equation. Now I'm going to go to the second equation. On the second equation, we have that y is equal to, or y is less than or equal to 2x, negative 2x, plus 7. Now, because it's not a fraction, I can make it a fraction. As I put it over 1, I have my slope, change of y, change of x idea again. So I want to start this graph up at a positive 7. So 1, 2, 3, 4, 5, 6, 7. It will cross at a positive 7, and then it's going to go down 2 units and then right 1. So as long as they're roughly close to our slope will be fine. And I also want to make sure, because the symbol on this one is less than or equal to, I want to make sure that I go and grab another solid line. And then I'm going to try to run my line through those 2 points best that I can. Okay, so now I need to know if I want to be on the top side or bottom side of that line. The safest way to test for that is to go back and use your 0, 0 point again. So what I'm going to do is I'm going to plug in 0, 0, 0, or the origin. I want to know if I want to be on the bottom side or the top side of that line. So I'm going to use that test point 0, 0 to help me confirm that. So I put in 0 for y is 0 less than or equal to negative 2 times 0 plus 7. Is 0 smaller than or equal to 7? That's true, and 0 is on that bottom side of that line, so I always want to go and shade towards the bottom side of the line. My solutions to this system is where the arrows are pointing towards each other. So where are the two arrows pointing towards each other? It's in between here. So this represents a solution set. So we're going to solve these systems of linear inequalities by graphing the region that represents all of the potential places that are solutions. And I paused the video just to kind of look, and I went and graphed these two lines. And this representation isn't quite as accurate as if you graph it on decimals or somewhere else. I think they meet down in here. But what I'm looking for is you being in the correct region. I'm going to look for is your y-intercepts correct? Or are your y-intercepts correct? Do your slopes look like they're going in the correct direction? And are you shaded in the correct region on those lines? So as I grade those, I'm not going to be real particular about are your lines exactly in the right place. They should be pretty close, and then I'm going to look at the region that you shaded.